Welcome to Team 4's presentation on system identification.
The problem at hand is that we are engineers designing a robot arm to be used in manufacturing cars. We are tasked with determining if our control model will give an accurate representation of the motor response for the two operation case conditions given here. The diagrams here are a representation of the equipment that was used to collect time, input voltage, and angular velocity data that was used in analyses of this experiment. A myrail was connected to an optical encoder to record signals that represented the angular velocity of the flywheel. For part 1, our goal is to determine the nonlinearities of our system. To start, 17 different input voltages were tested and various system characteristics were calculated, such as the steady-state omega, the characteristic omega, and the motor time constant, and they're all listed here in this table. The formulas used are also listed here. With this information, it should be noted that there is a linear relationship, as shown, between the input voltage and the steady-state omega. As shown here, a plot of the input voltages versus the steady-state omega can be used to determine the dead zone and saturation limits. For context, dead zone behavior is when Vn is too small to result in any rotation of the motor and is identified as when the steady-state omega is 0 for any Vn. In addition, we assume the dead zone to be symmetric about 0 volts. On the other hand, the saturation limit is the position where the steady-state omega stays constant even with increasing Vn, and in a physical sense, the motor will still be spinning at the same steady-state speed regardless of the increasing Vn. Dead zone and saturation limits are considered nonlinearities because the linear relationship between the steady-state omega and Vn is violated, or more specifically, the steady-state omega is no longer directly proportional to the Vn by the motor gain constant Km. As shown in the plot on the left, the saturation limit is 7.0 volts because starting at this Vn, the steady-state omega remains at 62 revolutions per second even as Vn increases. As shown in the zoomed-in plot on the right, the dead zone is between negative 0.1 volts to positive 0.1 volts because at this input voltage range, the omega steady-state value remains at 0.
This figure shows the angular velocity and input voltage data in the linear regime that is between the dead zone and saturation values. The voltage range of this linear regime is from 0.1 to 7 volts. In this voltage range, the time domain models are able to accurately represent the system response. The individual values of motor constant Km were found by dividing the steady-state angular velocities by the input voltages. The composite value of Km is determined by taking a linear regression of this data. When the input voltage is 1 volt and higher, the Km value associated with each individual voltage increases and is closer to the true Km value that is obtained from the linear regression. In the time domain model, Km was found to be 8.9459 revolutions per volt second. The low Km values below 1 volt are a result of the model not accounting for the signal noise and friction that the flywheel is more susceptible to at low voltages, even though they are past the dead zone. These figures of step responses show that as the input voltage increases, the steady-state angular velocity value also increases. Using the linear range of voltages determined previously, the step response plot was modified to more accurately represent the system responses. Values for the time constant Tm were found by determining the time when the angular velocity was 63.2% of the steady-state value. The composite value of Tm, which is determined by taking an average of the time domain Tm values, was found to be 0.1074 seconds. Below 1 volt, the Tm values are higher than the average as a result of the model not accounting for the greater signal noise and friction on the flywheel that is more noticeable at low voltages and causes the flywheel to take longer to accelerate. Individual values for Km and Tm varied even though they should have theoretically been constants. Since time domain analysis primarily depends on the input voltage for the system, this may be explained by discrepancies between the displayed input voltage and the slightly different voltage actually being passed through the equipment because of internal resistance and signal noise. Using the time domain analysis, the system response is determined by inputting the calculated Km and Tm values into the equation in the red box. When zooming in on the steady-state response, a slight variation in the angular velocity can be seen in the signals. These figures show the differences between the theoretical and experimental step response plots. The shape of the rise period varies between the input voltages in the experimental response plot, but the rise period of the theoretical plot is shaped the same for every input voltage. This results from the theoretical model assuming that Tm, the time to reach 63.2% of the steady-state angular velocity, is the same for each input voltage. The signal of the theoretical step response is also much smoother since they are a true representation of a first-order system and not affected by resistance, friction, or signal noise.
Here we are investigating the effects of adding mass on the Km and Tm values. From the table, we can see that the Km values decrease slightly with added mass. This is not expected because the Km value should stay the same since the steady state omega will stay the same even with the increased inertia. We believe this small difference can be attributed to error in the lab measurement and hardware. As for Tm, the Tm values increase with added mass. The increase in Tm is expected because the increased mass is causing the motor to take a longer time to reach steady state omega.
The chart below shows the frequency domain data for the system. As the frequency increases, gain and phase lead also decrease. This is expected since the system should follow a first-order Bode plot. Below are the experimentally generated and theoretical Bode plots for this system, along with regressions. The comparison to the theoretical Bode plot shows that we can assume this is a first-order system since the slope of the gain plot after the cutoff frequency is close to negative 20 dBs per decade. From the experimental data, a motor time constant of 0.1061 and a motor gain constant of 8.969 were determined. The frequency domain analysis is useful because it allows us to determine the motor gain constant and motor time constant even when the frequencies are high enough that the gain is not constant. The time domain analysis assumes a constant gain, so at higher frequencies it may not be accurate. The frequency domain analysis allows a cutoff frequency to be determined. This informs the range in which a time domain analysis can accurately model the system.
This slide shows analysis using the parameters found with time domain techniques. At 0.1 Hz, the system gain is very close to the DC gain and the phase lead is close to 0. On the other hand, the system's gain at 15 Hz is less than 1 and the phase lead is approaching negative 90 degrees. 15 Hz is well beyond the system's estimated corner frequency, so the gain and phase lead makes sense. However, looking at the experimental Bode plot reveals some problems with the time domain's assumptions. Extrapolating the regression line at 0.1 Hz, the estimated gain and phase lead are almost identical to those obtained using time domain techniques. On the other hand, at 15 Hz, both the gain and phase deviate significantly from the time domain's results, indicating that the time domain techniques aren't usable at those frequencies. In particular, the phase deviates so much that the phase no longer looks like it's from a first-order system. Now, the conclusions. The motor exhibits some nonlinearity, with a dead zone below 0.1 volts and a saturation zone above 7 volts. This limits the usable voltage range to between 0.1 and 7 volts. With regard to motor parameters, the Km and Tm values obtained using time domain and frequency domain techniques were very similar. Analyzing cases 1 and 2 show the shortcomings of time domain techniques. These techniques only work for frequencies low enough that it is valid to assume the system is first order with a negligible time delay. Frequency domain techniques, on the other hand, make no assumptions about the transfer function and reflect the actual response of the system. As such, they are suitable for both cases 1 and 2,